This is the last lecture, and what I'm going to explain today is a bit more recent topic. It's a recent viewpoint on the same problem that I explained in the previous lecture. And it appears in a couple of papers, these ideas. One is this article. No, actually it's not this article. Okay, it's an article by the Cipher group in DRX. I think the author is the same. So
I think it is too small to
too small. Okay, it's not this article, so you don't have to worry. So I think the first author is Van der Meer. The same one as the author is the same as here, Van der Meer, Cipher. I think it's the third author, the second now. Cipher. It appeared in BRX this year, 2022. The second, actually they're very similar articles. You can see, and the figures are almost the same. The second is an article we did recently. The first author is Pedro Aronari. Second author is Indian. I think one of the students are here. Roldan, who was in some time in STP, working as polyclinic. This is, by now it's an archive. You will also be here. Soon PRX, 2022. Okay. What I'm going to discuss is here's these two articles, and it's motivated by a previous article. Actually, this is 2008 article by the group of Bustamante. It says, you see here the title. This is an excellent article for students because you can learn a lot on solving biophysical models exactly. It's called exact solutions for kinetic models of macromolecular dynamics. So if you want to learn how to solve a continuous time marked process in biophysics, this is an excellent reference. Gemla, Fit, Bustamante. So this was a bit the inspiration to this work. At least in our work, I don't know if the one of the Cipher group was this one, Gemla, et al. J. Fisken, 2008. Okay. It's been a while for us to inspire us to develop this. This paper, apart from having a set of theoretical toolboxes that are extremely useful, apart from that, it has really a very important part in motivating problems. As you can see, the first thing that they do is they show simple kinetic models of molecular motors in which you can understand, for instance, I'm going by the button, but anyway, you can understand here that there are different states. There are different states, like configurations of the motor. Like, for example, could be the motor is unbounded, then there's ATP that binds to the motor, then ATP becomes ATP plus P. So these are like internal states of the motor, these ones. And then this is followed by a translocation step. So there is a step in which the motor moves along the x-axis. You see, the x dimension here is the position, like I was explaining before in the Ratchet models. Okay? So they talk about many different types of enzymatic reactions that can lead to motion in this way. And something very interesting is they try to connect this to real single molecule experiments. And within this paper, a very interesting figure is this one, which I'll try to explain right now, and why it's related to the problem I just explained. Remember that, as I said in my previous lectures,
the mic is striking your
sorry. Okay, this is better. Thank you. Remember that in the Ratchet models that I explained, there were always these two states, 0, 1, and there was the position. But typically, as I said, one cannot see the state of the potential, but one is left in single molecule experiments. You can see the position of the motor position as a function of time. Okay, this is typically what an experimental what a lab can do is to see step transitions, jumps. Of course, you need a very high precision accuracy to see these steps. Okay, so this will be a single molecule trace. What I explained in my previous lecture was about what if you just record the states, no? So you are in this state, and you are in this one, and you are in this one, and you just know the states. But as some of you asked, it is important to measure also the time. So typically, in good experiments, you have a sampling time, so you can record not only the state, but you can also record this. Okay? You can also measure time. So now I will do this step forward in trying to say what can we learn from the time statistics. Okay? And you see here that in this article, they were starting to be motivated by the fact that they see 4 types of what they call, this we can call intertransition times. Okay? Intertransition times. What is an intertransition time? Okay. We have a motor, and the motor can do only 2 things. Okay, as I explained before I was saying, okay, we see, this is the period of the motor, but before I was saying, okay, we can see different sub-steps in the motor. In many experiments, you cannot see the sub-steps in the ratchet. You can see only that it is either close to here or close to here. So this will be just stepping in sizes or step size of length d. Okay? You see that there are transitions that experimentalists can detect. For example, here is a forward. It's a jump of the motor forward, then a dwell time and another jump forward. And what they show in the first figure is the time spent between 2 forward steps. Okay? So you look at the motor, it makes a forward step, and you count the time until there is another forward step. This can be done in the lab, and this we will call it intertransition time. So you see, the first histogram that they show is the time elapsed between plus and plus. So that would be the probability density to find the time t, and let me call this plus plus. Okay? Plus plus would be, I did a step forward, and the next step was also forward. And if they have this distribution, they also can calculate the theory actually. But there are 4 distributions of this type. There is forward, back, forward, forward, backward, backward. So this would be 1 step backward of the motor and another step backward. And you measure the time in between. P of t. Let's say these are normal densities. Okay. Minus. And then we have also the conjugate one. So first a backward step, and then a forward step, and vice versa. So there will be also P of t plus minus, and P of t given minus plus. Okay? This will be information of times extracted from a time series of forward and backward jumps. And as I said here, the cost grading is even bigger because we just see, okay, not only we don't see the state, but also we see just that it's either in this region or in this region or in this region. It's even more minimal. So when we are in this situation that the information is reduced even more, time should be used in a very clever way to infer interrelationship. This is what I'm trying to show. Okay, so here you see the plus minus and the minus plus. Okay? Yeah.
Here. So because C and D graphs are not exactly the same, let's say the irreversibility, can you comment something about the irreversibility there? Because yes.
That's the question of this talk. I will try to see if I can use this, the difference between these histograms, to infer something about irreversibility or dissipation. This is a non-trivial question. Okay? In 1 hour, it's hard to explain everything, but this is the goal of this. I have this time series where you have just forward and backward jumps. So I record transition. This is a plus transition. This is a minus transition. This is a plus, a plus, a plus, a plus, and the time between them. So what I'm saying is that I record a time series. Okay, I just record transitions, which will be plus or minus, and the intertransition time, which I will call ITT, and intertransition times. Okay. What's the question?
So step length we are not changing, right?
We are
not
making
varying
minimal. Step length is over the same. Okay, so you see, when I record times and transitions, I can get these distributions, and I can also do something. Okay, these are statistics I can get. These are the intertransition times distributions. This is the ITT distributions. And I can also, of course, count how many transitions happen. So I can count how many pluses there are and how many minus. This will give me the frequency to CP plus and to CP minus. These are frequencies. Frequency of transitions. Plus, if this is Markovian, I could also take these type of things. P plus given minus, P plus given plus, P minus given plus, and P minus given minus. These are jumps, okay, or change sequence. Sequence, frequency. Okay. These are somehow all the information I could extract from such a trajectory.
Construct a two-state process.
It's a sort of two-state process because out of here, well, I'll show you later. Yes.
It's just the switches between.
Just switches. This is really the minimum I can get from a motor. Here at least I had 3 states. You know, I'm having just 2. And one is step forward and then step backward. But beware that it can be 2 step backward consecutive, okay? And 2 step forward consecutive. So this is what we are trying to extract here. Okay, the first question for my dear audience is the following. So if you see these distributions, the ones on the top, they are 0. So they have this type of shape. Okay. These ones look like this. So they are 0 for tau rotation. Okay? These are forward step. So there is a 0 probability to do 2 steps forward in time 0. However, if you look at the other distributions, these 2 that are here, they have a totally different shape. So they are decaying. Okay? So they are, the most likely time is 0. Okay. Another question is why this is happening. If anyone has an idea, because there is a clear difference in shape between them. Very big difference. Okay. This is not so trivial. And this is somehow a signature of hidden structure at the end. Because if you think about a motor, for example, you could say one of these cases, you want to have.
Just to clarify, so what you have got a distribution of the residence times, right?
It's not the residence time, it's the time, well, in the end it's residence times as well. It's residence time, but, because these are 12 times. But in the end, here is the distribution between 2 forward steps. There could be hidden structure, so there could be more states that we don't see. Maybe you're creating a model which has more states. So the key answer you can get it from considering an example. So if you have a 3-state model that has jumps, you may have like 0, 1, 2, say this, and then imagine that this transition is the one that involves stepping. Okay, you can either do it like this, say, one way is saying, I don't see this, I don't see this, I only see these transitions. This is one way of explaining the setup, and all this is hidden. It is hidden. Even the states are hidden. This could be one way of explaining. Or another is like they do in this paper, right? 0, 2, 1. Like this. These are the hidden. And then this one, when it goes forward, it arrives here to 2. And when it goes backward, it goes.
Because if it is only 2 state, it is likely that it will be the ones below, right? More exponential.
What?
If it is only like 2 steps, it will be likely that they are exponential, right?
So it's not that trivial because of the following reason. Imagine this is hidden, all this is hidden. This is hidden, okay? If this is hidden, and you can see this one plus, or this one minus. Then, in order to see plus plus, what you need to do? You need to jump here, and then travel the network again. You have to come here, come here, come. So making this in time 0 is infinitely, extremely, the probability to make this transition is extremely small because you have to travel the entire network. Okay, that's why, and the same backward. Backward minus minus would be 2, 1, then 1, 0, and back. And then this, in the end, it means you need to make a cycle in time 0, which is not wrong. So that's why you have this meaningless. Okay? That's for plus plus. For plus minus, it's totally the opposite. Plus minus would be here. I come here, and I come back to the same link. That's the most likely, rather than traveling the time network. Okay? So that's why they have different shape. Okay? So this is a bit the first thing we can learn, that we just observe these distributions. If they have this type of different behavior, it means there is a hidden structure with more than one state.
Just one simple question. If, for example, Luca is top, standard model we say that you have model like it's a bias random walk. You take forward step and backward step. So there, for example, you have plus plus, minus plus, and all possible combinations.
Then yes.
Right?
Yes.
So then, but that is also just plus and minus, right? So
yeah, but there's nothing else than plus and minus, and they're all exponentials.
There everything is exponential. That's the key point.
Here, there's no exponential. Okay. If you consider the time between backward, it's not exponential, and also the other one is exponential. Of course, if you take
No, the only point I was making was that to go from plus plus to minus plus minus, you can have a two-state process which can do that, so long as there is also. That's all the point I was making.
You could, depending on the distributions. Yes, depending on the distribution. There's some distributions that you cannot obtain. I'm not sure. I'm not sure you can get this with a distribution. It's a very good question. Very, very good.
So when I look at this picture, do I have to remember the same states that you drew in the last lecture? Like 0, 1, 2 and...
This can be totally different. This is totally
different. This is the generic three states.
Generic state. I'm trying to go in a more generic description now and have consider models that are like this. Okay? There are cycles, and some of the steps in a cyclic network, some of the steps involve spatial motion. All the others do not.
But sorry,
Okay.
why can't I have 2 steps? I mean, the second step can be the next side, right?
Sure.
Why do I have to come back all the way? I don't understand.
What? Come back?
Those 2 positive steps, you said that in order to take that, I have to complete the cycle.
Yes. You have to complete the cycle because for the plus will be 1 to 2. Then if you want to complete another
But
plus.
then I go to the next time, again plus, next site.
Like you have
Yeah,
shown
but
in
these transitions are invisible to me. So the only way I can make 2 plus transitions is I do 1 to 2, and then I have to go to state 0, state 1, and do it again, because of the topology. Let me show you another example, like maybe a more biological example could be, okay, for example, kinesin. Kinesin, we have this type of cycles. There are many examples. So this is the example of dynamic, which is totally cyclic, unicyclic, but you can have molecular motors that have this type of structure, where the motor can do a step forward, a step backward, following a ITP hydrolysis. So, for example, in the cycle on the top, what happens is it moves backwards due to ATP synthesis, and in the one in the bottom, it moves forward due to ATP hydrolysis. And there are different. So these are somehow like there are 2 legs of the motor, because this is kinesin, so it has 2 different legs. And there are many of the transitions are just configurational. So it's either ADP, for example, 2 to 1 means ATP has been bound to the motor. 1 to 6 is the hydrolysis has started and phosphate is released. And 6 to 5 is ADP is released from the motor. So you see, this is a complex Markov network to describe the motion of a motor. Then once this happens, the motor makes a motion freely. So this is a model that includes both ATP hydrolysis, that is decoupled from motion. So it's a motor that first burns the fuel and then makes a step. So there are 2 cycles. You can cycle one way or another, forward and backward. 2 to 5 is a step forward, and 5 to 2 is a step backward. This is an experimentally tested model for kinesin. What you see here is there are 2 cycles, and most of the transitions, you cannot see them experimentally, because you cannot see the binding of ATP. But, so the only accessible transition is this 2,5 and 5,2. It would look like this single molecule trains, in which there are many hidden states. You don't know how many. You don't know how many. But I tell you, if here you want to do 2 plus transitions, you will have to do 2 to 5, and then you have to do again 2 to 5. So the only way to do 2 to 5 is either burning ATP or synthesizing ATP. And this takes time. Okay? That's a big point. And you need to travel the network a couple of times. Okay. Alright, so now I need the help of someone to connect this.
Experimentally, we don't know, we can't observe 1, 6, 3, 4 states.
Experimentally, in this model, you only see 2 5. And this makes things good. So when a motor is multicyclic, things become much harder.
So you mean 2 and 5 of the position axis, and
2 and 5,
is
2
the
to 5?
position,
Yes.
everything else is canonical.
Yes, yes. This is not Frasen-Ratzen model, it's another one. Which, so Frasen-Ratzen is a specific model, but I talk about generic concepts that can be applied and illustrated. Now I'm talking more about enzymatic reactions in which some of the steps involve spatial motion. Okay? So now let me go a bit with some brief calculations that I'll try to show you, to illustrate what can one do with these time streams. Okay? So as I explained, now I would say we have continuous time, first point. No, I don't need it. No, because there's only one. So we have continuous time, and we observe transitions. So the information that we retrieve from such an experiment is a time series of times and transitions. So I can call that time series gamma tau. Okay, I will not enter too much notation because otherwise we will level it. And we will see the first transition at time t0, the transition L0. Then after a time t1, we will have transition L1, etc., etc., etc. Up to, okay, there's time t2. These times can be different. This is just a sketch. up to the final is Tn plus 1, okay? The Entransition. And the total time of the trajectory is the sum, is tau is total time, the sum I equals 0 and minus 1 of t. Okay. This is the total time of the trajectory. Then the Li here is the transition, the ith transition that I observe. So each of these can be either plus 1 or minus 1, plus or minus 1. Okay? Plus 1 or minus 1. Okay? And the time can take any value, so each of the times can be between 0 and infinity, such that the sum of them is the total time of the trajectory. So what are the fruits that I get from here? Well, the fruits, what I can extract from this trajectory, is the probability for the transition, the joint, so the conditional probability that I see a plus after a minus, and the intertransition times distributions. Okay? And recall one thing, that these are normalized densities. So each of these think of t given Li minus 1. These are integrated. If you integrate from 0 to infinity, you get 1. These are normalized densities. Okay. So the main result that appears that we derive in our work and also in the work in the group of Seifert is about the Kullback-Leibler or the irreversibility in these time series. So typically the transition, the time series of transitions typically is Markovian. So if it is Markovian, we can compute the probability for one of these trajectories. Probability for one of these trajectories, this transition space will be the probability of times t0 to tn plus 1 and transitions. L0 ln, and I will call this the vector t, and I will call this the vector l, for simplicity. So one can show that this, with Bayes' theorem, this will be p of vector l times p of vector t given vector l. This is simple to show. And moreover, the p of this is not the nice. P of vector l is p of L0, p of L1, L0 up to p Ln minus 1. This is the first part, and the second part you can write it TTL T given L will be p of this. Yeah, actually, this I have to be careful. P of T1 L01, P of T2 L1 L2 to P of Tn L n minus 1 L. I think it is 1. Okay. Okay, so this will encode somehow the probability for such a trajectory. And now, remember, when we look at irreversibility, we would like to do the probability of the time reversal trajectory. Now we are taking the time reversal, so we need a trajectory with time reverse, and we look at the trajectories that appear. So this is a bit non-trivial, and the key point is, okay, this is gamma tau, and now I would like to know what is gamma tau tilde, which will be the transition time series associated with the time reversal trajectory. Okay? This is not going to be just picking this and time reverse. No. It's going to be time reverse the original trajectory, that one, and see which trajectories or which sequence of transitions and time to get. And this is a bit tricky, but it's the central part of the article and of the work, is that I will get a new time series in which I will call, for example, T0 tilde will be the time up to the first transition L0 tilde in this time series. This is just notation. L1 tilde, T2 tilde, etc. up to Tn plus 1 tilde. Okay? This is the way, okay, I just put a tilde everywhere. Now the important thing is this T0 tilde L0, how they are related to this sequence. And this requires a little bit of work, and making a simple example you can figure out on your own. So imagine if you can see only the transition 1 to 2, you can have something like this. So you have state 1. Actually, I did 3 to 1. Okay, 3 to 1, 1 to 2. Okay. So let me just show you what I did in my calculations. So for me, this will be 3 to 1. But anyway, this one. Okay, this is my forward trajectory. So in my forward trajectory, imagine I can only see this transition. Imagine I can only see 1, 2, 3. If I can only see 1, 2, 3, I can see this transition backwards or downwards, this transition upwards, and this transition downwards. Okay, I have to read the time series from left to right. So I go like this, I go down, then I go up, and I go down. Okay. Now, if I time reverse the trajectory, it means I start from here and I go backwards. So now, if I go backwards, I first go up, and then I go down, and then I go up. So the transitions have changed. So they have changed sign. The one which was plus now is minus. Okay, so it's a bit tricky. But if we go backwards, in reality what we get is we start. How can we do? The first time is the time that we have here. So this would be n plus 1. The first transition we will see, if the last transition was plus in the forward, it will be minus. So we will have a minus L n. Then we will have T n minus L n minus 1. So if it was a plus, it becomes a minus. If it was a minus, it becomes a plus. Okay? That's why I put the minus. Etc., etc., etc. Up to minus L1, T1, T minus L0. This is the last that I see. Okay? So now I have to compute. So I have this, the probability for this sequence, divided by the probability for this sequence. So this is the original transition forward, and the backward is like this. Okay? So this is the way you do the transformation. Times, okay. You see, so now, okay, you can do this at home. It's not that complicated. Now, what I can show is that one can now compute the Kullback-Leibler or irreversibility in the sequence. And this is gives very interesting results. And it shows you that you can do some inference about the hidden states. And these are some properties about the hidden states. Either, for example, if the hidden network is cyclic, unicyclic, or multicyclic. Okay, so if we say that the total entropy production will be greater or equal than what I will call sigma L, this is the Kullback-Leibler with these path probabilities for sequence. Okay, this one will be log ln probability gamma tau by probability gamma tilde tau divided by 1 over tau. And this, I can write it as sigma small l plus sigma t. Okay, and let me just tell you what is sigma l and sigma t. So, sigma l, I'm simplifying a lot there because the first thing you see is that in the path probability, sorry, in the probability for a trajectory, what is the probability for a trajectory? The probability for a trajectory, the first trajectory will be this quantity times this quantity, PL, PTL. So I will have a sequence of PL 0 and 1. So this is a sequence of letters. So the irreversibility for this sequence, Markovian sequence of letters, will be D2. But I explained this one. D2 in the space of L's. And the irreversibility for the second part will be a bit more complicated, which I'm going to show. So the first part will come from the PL, and it turns out to be, sigma L is like a V2. Turns out to be the following: the sum over Li, the sum over Li plus 1 of P Li plus 1. This is the D2, what I explained in my previous lecture. P Li plus 1 given Li, P Li given I. Okay, this in reality is what I called this morning D2, but for transistors. Okay, this is what I call sigma. So, and this is wrong because I missed this.
Log.
Okay, it's very wrong. It's wrong. Oh, see. Yes, you know it's equal to 0 or to 1. Log of the ratio. But, okay. First of all, just realize that we have to sum over Li plus 1. The transistors can be plus 1 or minus 1. Both. So this is P plus plus, log of P plus plus, divided by P minus minus. Here we have to put minus it. So this has 4 terms. P plus comma plus, log of P plus given plus. Here minuses. P minus given minus. Then there is the same thing with minus. P minus minus. Log P minus minus. P plus plus. And now there are other 2 terms, plus minus. But the plus minus terms are 0 because you get plus P plus minus log of P plus given minus. And now you change it, so you put the Li here. P minus times minus is plus. You get this. This is equal to this. This is log of 1 is 0. So that's it. Because also the minus plus doesn't count. So this is the result. It's a D2, but it's simplified. You only need the statistics of 2 consecutive steps forward and 2 consecutive steps backward. It sounds a bit counterintuitive because you would say irreversibility is forward versus backward. But okay, this is contains irreversibility because plus plus is irreversibility and minus minus is also.
Another direction.
Yes, that's right. Exactly. That's so again, this can be written in a simpler way, maybe P plus plus minus P minus minus log of P plus plus given plus P minus given minus. Okay. This is the current in the transition space, and this is like an affinity in the transition space. So you see, if you see the same amount of plus and minus, this quantity will be 0. So still, if you uninstall, this quantity again will be 0. But this is equal to 0 at stall. Otherwise, it's greater than 0, this quantity. So we arrive at the same problem. Even if we are measuring continuous time, at stall, we see nothing, just counting transistors. So then it comes to one of the key insights that one of you was asking, what about the time? Does the time help in this case? Okay? And the answer will be revealed in a moment, or I hope the answer is revealed to you, because now the second part, which is about times. The second part is defined similarly, but now it's concerning this part. So it's 1 over tau times the Kullback level of t. Now it's t vector, L vector, and now we have to put, okay, the t vector tilde, okay, it's a bit heavy the notation, and then L tilde, L vector tilde in the time reverse. Okay. So when you do this, this becomes, this takes the following form. Again, there is a sum over Li's and Li prime. Remember, these are the transition at I, and this is the next transition. N plus 1, P. So again, you average also with Li plus 1, similar thing. And now, what enters here is going to be a bit more complex than this. It is itself a Kullback ladder. There is inside here a Kullback ladder of P, T, Li plus 1. So now the time appears. It is going to be the Kullback ladder of the time distributions, the intertransition times. T, and now it comes minus Li plus 1 minus Li. Okay? And okay, now it's a Kullback ladder in time. In time. So our random variable is not going to be else. This Kullback ladder takes the form dkl. Sorry, the best is I write it on the left. Right? Not mine. This Kullback ladder is a bit different because it looks. This is for time densities. This is KL, P, T, Li. Li plus 1, given P, T, minus Li plus 1, minus Li is the integral between 0 and infinity of dt, pt, Li plus 1 log of P, T, Li plus 1, P of T minus Li plus 1 minus Li. Okay? This is the Kullback ladder. So these are time densities, and then you do the Kullback ladder of T plus plus, T minus minus, for example. Again now the same story will happen that I show here. The same story, because there will be minus, so the same manipulation. So there will be the Kullback ladder of plus minus, and plus minus is 0. So again, in this part, these are 4 possible sums: plus minus, plus plus, minus minus, minus plus. But the plus minus sums are going to count 0. So the only thing you get is this 2 Kullback ladders. So it will be P plus plus. Let me write like this: minus P. Is this correct? No, it's not correct. You cannot write it like that. It is, need more space. Is P plus plus. Then this Kullback ladder, which you can write like this: 0 infinity dt P T plus plus log of P T plus plus where P T minus minus plus P of minus minus integral 0 infinity dt P T minus minus log of P T minus minus P T plus plus. This is the formula. So again, the only transition that contribute to reversibility are the so-called repeated transitions. Repeated transitions. Okay. Please. Sigma t equals 1 over tau of this. Tau is the length of the trajectory. Yep. P of t vector tilde, L vector tilde. Is the t and the L associated with the reversal conditions. Make sense?
And the t vector, you converted it to a scalar t because that was the, I did not get it.
Sorry?
The t vector,
Yeah,
you
so,
converted it to t.
so the key point here is that in the forward trajectory, there's a t vector of t0, t1, t2. In the backward trajectory, I call it t0 tilde, t1 tilde. So this is nomenclature, it's just notation.
Yes, just a reverse.
It's just the reverse of the times.
Yes.
I just call it like that. It's just that t0 tilde is tn plus 1
Got it.
because I'm reading backwards.
Yes, yes. No, I got it. Okay. What I'm saying is that there is a t bar vector which is a collection
It's a collection of
and
times.
is equal to then that bar you have removed from the p of.
Yeah, because here I already have used this thing. I have used this. The tilde is this. It's not one step, okay? It's a couple times.
I cannot write.
Okay, so
It's okay.
1 hour is ready.
Yeah, no, it's okay.
But you are time reversing the times. And this time reversal of times, okay, this is not one step. So it's several lines. Okay. So it becomes P of one transition, the next one, and then the pullback glider of repeated transitions.
I see.
That's the final result for sigma t. This is what I want to compute. I have the probability for the first, then I compute the probability for this one.
I got it. So front to back t, back to front t,
Back to
from
front.
2 time steps. Okay.
Exactly.
That's why it becomes just t.
Yeah, it's two transitions always. Okay? These t's are two transitions. It's the time, that's why it's called intertransition time, because it's in between two transitions. There is transition L1, L0, transition L1. I'm measuring the time between two successive transitions. Okay, this is the t. All it is. Okay? So, this is the result that we get, and we see that repeated transitions are essential to reveal irreversibility or dissipation, length reproduction. And see that very important is to know that at stall we can still see reversibility if these two are different. So if we have a motor at stall, it has no current, we would be able to see irreversibility if we get that t plus is different to t minus 1. So main message from this part is if we are at stall, if at stall is no zero current, next we can predict irreversibility. We will predict sigma t greater than 0 if p t plus plus is different to p t minus 1. Okay? So you take a motor and you count the time between two forward steps, and you count the time between two backward steps, and you build a histogram. Okay? Let's look at the histogram. The motor moves the same times forward and backward. But it could be, one thing is the number of times it happens, and the other thing is how long it takes. So it could be that it moves very slowly forward, and it moves very quickly backwards. Okay? So the number of steps forward and backwards could be the same, but still the times could be different. So now the question is when this happens. And this we did started to do simulations and see that in some cases at stall we have t plus plus is equal to p t minus minus. Okay? And this happens very importantly when the hidden network is cyclic. There is only one cycle. So if the network is unicyclic, so you have an enzymatic reaction like this, okay, in which you only see this transition, unicyclic. If you are at stall, these are equal. Okay? So at stall, in a cyclic, unicyclic enzymatic reaction, you can see nothing, no errors. But if you take a simple model of a multicyclic chemical reaction in which you see enzymatic reaction, where you see only this transition forward and backward, in the multicyclic case, these distributions are different. So P, T plus plus is different, P, T minus minus, even at stop. Okay? So the take-home message is you can learn entropy introduction from at stall, so without currents, if the system is multicyclic. So this is a fundamental result, but it's also thermodynamic inference, because you can just do this experiment if you see only one transition. From this observation, you conclude that the biological system is multicyclic. The hidden structure is multicyclic. The structure is multicyclic. This is in the end thermodynamic inference.
How many cycles?
So how many cycles you cannot guess with this one? This we cannot guess. For this you need other techniques. There are.
Like theory like this.
Similar, yeah. There's a paper by Arato and Seifert called, I think it's called Skewness and Kurtosis in Stochastic Thermodynamics. So measuring skewness and kurtosis of a current, a current, you can infer the number of hidden cycles. Yeah. Nowadays, also the number of hidden oscillations. You have a oscillation system with oscillation now. Coherent oscillation, we can also use that to infer the number of hidden.
So like the experiments.
Experiments, I don't know. This is very recent results. Experiments, I don't know by now. These are, as I'm saying, these results are very, very recent.
So this is from the Seifert paper? Or?
All this is in our paper and Seifert paper, the one I showed at the beginning. This 2022. If you want to infer the number of hidden cycles, it's another paper by Roldan and Seifert. Not this year, this is older. It's called Skewness and Kurtosis in Stochastic Thermodynamics. Very short title. Very nice paper. Very nice paper. And okay, with this, we learned something. I can show you some examples briefly.
Are there other experimental systems where this plays out rather than motors?
Yeah, of course. This is a generic. So what I'm showing here is a generic treatment. So it's.
But do you know any other experiments which can be related to this model?
So
proofreading probably is one of them.
Sorry.
Kinetic proofreading process. I have heard these kind of cycles.
Yeah, of course. In that case, you know, stepping. So to me, it comes to my mind in stepping, and this is what I know. But okay, it's not principle. The analysis that we do is for all one process. So any experimental system that has a Markovian dynamics and it has this transition, one visible transition or few visible transitions. Because today I talk about only one, but you can generalize to few transitions. It could be that you see two of them when you see 3 of them. So one can do the analogous theory for more than one transition. So this is actually in our paper. It's generic for more than one. The key point is seeing only a few of them, not the entire collection of transitions. So just wanted to show you this simple example. So you can, as I said, if you have a cyclic, unicyclic transition, you get that the distribution plus or minus are the same. This is a very simple simulation. So you do continuous time process, you just track the 1, 2, and the 2, 1, and you see they are exactly the same. But more interesting is when you have multicyclic. In a multicyclic process, when you see only one of these transitions, in general, the plus and minus distributions are different. These are simple simulations you can show. And this.
If the two halves are symmetric to each other, then they will be similar again, right?
Yes. Yes, you need some asymmetry. And actually, this figure is almost the same as what I showed you in the previous lecture, that you can tune the bias parameter to a point in which you have no current. That's the point that I show here. And again, here you have zero entropy production. This is like the stall force. This is stall force. And if you apply the thermodynamic acceleration at the stall force, so the thermodynamic acceleration is this one. It gives zero. So it's when there is no current, TOR is not informative at all for the entropy production. And then if you apply our two measures, the sigma L, sigma T, so the sigma L is the lines, so it's this one. So the sigma L is also measuring currents, and it's also equal to 0. It's the dash line, so this one. Yes. However, the time, the sigma T, sees the asymmetry. Even at stall, the sigma T, which is the dotted line, is here. So it really gets close to the entropy production. So measuring intertransition times is very useful in situations where there is no current. So another take-home message, I insist that the current is not all. So it's 3-time correlation, so what I said this morning, reveal irreversibility. But also, if you see only 2 types of jumps, you can see reversibility with the time. This is quite nice. Okay.
So when current is 0, this time statistics.
The time statistics are
Give you
useful.
that irreversible.
Are useful. In the lecture this morning, there was no time statistics. I was cutting. I was just seeing the jumps.
They are points.
Exactly. But if you can track time, this time is useful to revisit.
Like estimate the dispersion.
And we were not the first actually to realize that fact. There's this Nature Communications paper by the first author is Kili Bisker. There's also Parondo. This Nature Communications paper, they were already understanding this. But there, they were using the they were not measuring intertransition times, but the time between 3 states. So it's a bit more complicated, the analysis. But the conclusion is the same. The conclusion is the same. At stall force, current is not enough. So either 3-time statistics, what they do, and what I did this morning, or intertransition times. So,
but what about like, so these are for like discrete.
by the way, I forgot to say that this is the total entropy. This one is sigma T, the black one.
So these are for discrete trajectories, like
This continuous time
continuous time, but you have this
in discrete states.
Discrete states.
In continuous, I haven't done, I don't know. Maybe even one extension, but continuous, I don't know.
So actually, if the detailed balance is not broken, and we still have this cycle, still you have to go through the entire cycle to see 2 plus, right?
Yeah.
So would the distribution look the same? But you have assumed here that you have some finite current in the circuit.
Yes. No, I put arbitrary rates. So here, it's not that they are finely tuned there. Arbitrary rates, you can find this. It's very general statement. It's not a very specific example where you will find this difference between these two. It's not very specific. As long as there is a little bit of asymmetry in the rates, that the the top cycle is not exactly the same as the bottom. In general, you will see them different in this multi-cyclic.
This one, so the sigma t, is that also an indication of that you are burning ATP, for example?
It could be. It depends on the motor. Some motors use ATP, but it's true.
No, it's stall, for example. Like when there's a zero current
Yeah.
in velocity,
Mm-hmm.
and but you see sigma t which is non-zero.
Mm-hmm.
So you are always burning ATP for a motor, for example.
Yeah.
So can one say that if ATP is being burned, then you will always see sigma t to be non-zero because some entropy is being produced?
Yeah, in theory, yes. But if you burn it in a cyclic way, like here, then
You may still burn, but it doesn't matter.
then you may burn it and still don't see.
But then there is some contribution of entropy is missing, right?
Yeah.
Because you are
Yeah, in this way, yes. In this way, when you are unicyclic, you need to take a current.
Yes.
If not, you have nothing to do. You could think about this D3 that I talked this morning, but in this case, it's a two-state, so it's forward, backward. So you will need a third state at least to see ATP burning in a unicyclic. You need three states. If not, it's a bit of a conclusion.
So just with
Yes. Yeah, actually, we have a case. We have a case that is multi-cyclic, but the two cycles are equal. So I think this is what you're saying. They are totally symmetric, and in that case, they are the same.
they are identical, right?
They are identical in that case.
But you may still be burning ATP at stall.
Yes, you may still burn. Yes. So yeah, I'm almost done. I just wanted to say that entropy production is also useful to estimate efficiency of motors. So there is a very simple estimate of efficiency in motors that is very, okay, you can define it in many, and this type of equation that relates from a thermal motor, this is the efficiency, which is related to the power that the motor does when moving the filament and the entropy production. So of course, if you get better and better estimates of the entropy production, you will get better and better estimates of the efficiency as well. I'm not going to explain too much on this, but you can take a look in the paper. And finally, just to say something on, this is the plus plus and the minus minus. There are also the plus minus minus plus. So you can also think about, okay, these are the repeated transitions, they are the same, but there also exist the so-called alternating transitions. Okay, this is going to be very, very quick. The alternating transitions do not matter for irreversibility. So you can do a histogram of this one, the P plus minus, and the other one, which is the P minus plus. This we call alternating transitions. And this, as I said, they don't contribute, they are useless to estimate irreversibility. They serve for nothing. They don't appear in the formulas. But you may wonder when these two are different, when they are equal, and so on. And what we found in very simple models is that these two are different when you have disorder. So if you have a motor that is doing cycles, so here, okay, I put it in a line, but this is like having cycles. This is 4 states, so this is like having 1, 2, 3, and 4, and I only see one transition. Imagine that this transition moves me to a next network that has a different color. Let's say this one is blue, okay? And this transition moves me to another one that could be, okay, this one was red. Imagine I have this type of disorder, and I don't know a priori that there is a hidden disorder. So I just see jump forward and backwards, but there is hidden disorder. In these situations, these two distributions are different. You can show with simulations. You can do simulations of a sequence of networks that are drawn randomly. It can be type A or type B, and show that in that case, is, in that case, when you compute the curvature library of alternating transitions, which is this one in magenta, when you make the template more and more heterogeneous, this curvature library is increasing. So the more heterogeneous is your hidden network, the bigger is this asymmetry. So the asymmetry between these alternating transitions is a signature of disorder. So this is another story. I don't have so much time to explain.
Disorder means in the schematic, disorder is a microtubular cell.
Yeah. So it could be many things because this is just a network model. Okay, maybe I can draw it a bit better, but this is a network. Okay, so you see here. So this is a network that can be blue or it can be red. Okay, and then the blue or red color is drawn at random. The stochastic process, IID. So as I said, so you have the blue network, maybe 3 states, and then when you jump forward, you jump maybe in a red network that has different rates. And when you jump backward, you will come back to the blue. But then from the red, maybe at the next step you find another red. Okay? But this is hidden to you. So the only thing you see is these forward and backward steps from these 2 states. So the more disorder you have, the bigger is the symmetry with this distribution.
So when you were showing the initial distributions of these 4 things,
Yes.
these 2 are asymmetric, right? So you had some disorder there in your simulations.
Good point. It's not clear because these ones are not. Actually, I bet that these are the same. I bet that, and they are actually the same. Yes, look at them. Okay?
The statistics are not
Looks different, but I think they are not really related. But they are exactly the same. Look, 10 to the 5, up to 25. Okay, this is in log scale. You see, they are the
The
same.
initial fall seems small.
Really? Okay, one has to check a bit. Okay. It's a fully reversible linear kinetic scheme. Okay, so I don't have to double check, but to me they look very similar. Wait. No. Okay. That's plus. Plus minus plus. Okay, well, one has to check, but a good point. Maybe it's wrong. Or maybe my paper is wrong. I don't know. Okay, it's a simulation to always take the simulation careful. Yeah, it's true that the decay is different. So, well, I will have to check, but I would have expected that they are similar.
I mean, it falls down to 10 to the part 2 at beyond 28 or something. Where indeed it falls.
No, yeah. You're right.
So it is different.
It is different. Okay, so I have to check. Which model are using it. I know the one in my paper, but maybe here it's one. Good point. Very, very good observation. The other ones are clearly different. You see, no? And this one reverse. These 2 are different, so we will use the formula and say how much dissipation is in the motor. Right.
because this is not at store, right?
This is not a store.
So P++ may not be symmetric.
No, yeah, it's not a store. Exactly. It's very good to have experts here. Bravo. So the next lecture, you give it.
Not an expert.
Very observant student.
Huh?
Very observant student.
Yeah. I know.
I think there is some saying about some million monkeys like typing, producing Shakespeare, right? So I'm just watching this lecture was so long in time. And you for saying something right.
What is it disorder?
Sorry?
Structure
Yeah, I was thinking in for example, DNA polymerase, which is reading a DNA template, which has disorder because it has A, T, C, or D. So the right
arrangement.
Yeah, the template is for polymerase. It's DNA polymerase.
Yes, there may be, but what kind of disorder, like hydrazine or those kind of focus where there what is that?
And there, disorder is a bit less clear, but because you assume a periodic filament, homogeneous. Disorder takes a lot of sense when you think about copies,
In case of polymers, it's like a
proofreading, etc.
There's
Yeah.
tracks, so
I think proofreading on template-directed normalization.
But here only that figure, when it was the microtubule, I thought the ENT were like ATP or, sorry, GTP or GDP bound tubules.
This is not experimental.
No. The other figure that you were showing the model working over the microtubule.
That's not also experimental. This is a simulation.
But disorder was those ABs.
A and B's, simply. And A was a network with rate matrix W, and B was a network with rate matrix alpha W. So it was a very simple disorder.
Yeah.
Very
But so
simple.
I'm thinking that there are these models that microtubule where the tubulins can be thought of as ATP, GTP bound or GDP bound. So A and B can stand for those
Could be.
states of the
Yeah. So applications are extremely welcome, and I think most of you know much more about specific biological systems, but you can find good problems. So we need very generic models. We applied some of them that were